So hello everyone, welcome back to the ARC seminar this week. Today we have Andrew Laeuger, who will be talking about the gravitational rainbow today.
Cool. Thanks everyone for coming. Really this is just going to be sort of a gravitational grab bag of sorts with an introduction that serves to offer some sort of through line, but then it'll go totally all over the place. Okay, so first I need to take a moment and acknowledge that the electromagnetic astronomers out there have had it really good for quite a while. Of course, there was a bit of a lull between the first telescope in the early 1600s and when they finally got their act together and started expanding outside of that visible band. So I guess within the last 100 years or so, there's really been this expansion across many orders of magnitude and frequency, and by extension wavelength, that we can probe with electromagnetic observations. Now, of course, we've had radio astronomy for almost 100 years now, and you guys still can't really tell me what an FRB is. So there's ways to go. But with this in mind, we are sort of living in an age today where the field of gravitational wave astronomy is finally starting to expand out of its the first band that was detected. So let's get into that a bit. So now the gravitational wave spectrum, what is there to find? I've conveniently plotted a log scale of frequencies here, and I'll sort of fill this frequency band here with some various sources. So of course the most common source of gravitational waves out there is compact object mergers, primarily black holes and neutron stars, although white dwarfs can source gravitational waves as well. It generally goes that as the larger your object is, the more slowly it's going to inspiral with another compact object, and thus the gravitational waves will be lower in frequency. So at the very low frequency range, we have supermassive black hole binaries, perhaps from the mergers of two separate galaxies. These create nanohertz gravitational waves, which is a period of about 30 years. At slightly higher frequencies, say microhertz to millihertz, we might find extreme mass ratio inspirals, or EMRIs. Going to higher frequencies, we might have white dwarf binaries, which will be very common in our own galaxy. Going even higher in frequency, we have stellar mass object mergers, which have been detected over 200 times at this point. And even higher frequencies, we can have smaller mass compact objects, such as subsolar mass black holes, which have a number of proposed formation channels, one of which is that they were formed in the early universe, making them primordial black holes. Beyond this, we might find core collapse supernovae producing gravitational waves in the kilohertz band. These gravitational waves come from the oscillations of the proto-neutron star remnant. At very low frequencies, quantum fluctuations during the Big Bang could produce gravitational waves with frequencies of 10 to the minus 17 hertz, since they've been redshifted to today. And finally, there's a number of exotic sources for gravitational waves that are somewhat hypothetical at this point. So for example, the axion dark matter candidate can form clouds around spinning black holes that behave much like the electron wave functions around a hydrogen nucleus. And the annihilation of these axion particles in the clouds can produce gravitons. In other words, energy from this from the spinning black hole is carried away through the axions as gravitational waves. And these gravitational waves generally scale with the mass of the axion. And for theoretically well-proposed axion masses, this lies somewhere in the high kilohertz range. Other sources like early universe phase transitions and cosmic strings could also source high-frequency gravitational waves, but I couldn't find a good way to draw on the skittles. This is where the skittle drawings end. Okay, so with these sources in mind, it's convenient to then talk about how we are searching across this expansive band of frequencies. Gravitational wave astronomy actually started with resonant bar detectors back in the late 1960s and has continued through today, although there haven't been any confirmed detections using these detector models. What Joseph Weber most famously looked for is he had this massive aluminum bar and a gravitational wave which shrinks and stretches the object should produce vibrations that then can be picked up with some electronic transducers. He claimed to have found gravitational waves. No one could reproduce it. We don't believe that he did. Now, of course, what everyone generally knows about are the ground-based laser interferometers, such as LIGO and Virgo, and hopefully CAGRA within the next few years, maybe. Confirmed detections began in 2015, so just about 10 years ago, and the landscape is really improving. Within the last couple years, we have finally expanded out of this hertz to kilohertz band and gone all the way down to the nanohertz to microhertz range with pulsar timing arrays, which carefully track the arrival time of the radio waves from pulsars at various astronomical distances. And as a gravitational wave comes through, it slowly changes the arrival time of those pulses in a way that can be correlated across the sky. And with many observations, with many radio telescopes over many years, we can extract some very low frequency gravitational wave background. And this was confirmed in 2023. Now getting to sort of the future concepts, still within the domain of ground-based interferometers, there are some proposed upgrades to the LIGO detectors, so just adding in cryogenics or upgrading the mirror materials, various things to sort of continue to push down the noise floor of these detectors. There are also some plans for larger interferometers within the next couple decades, such as Cosmic Explorer, which will be a interferometer that's about 10 times the size of LIGO, and Einstein Telescope, which will be in Europe, which is an equilateral triangle, but also larger than LIGO. And that will help us probe frequencies sort of in the same range as LIGO, but also a little bit below and a little bit above, and with better sensitivity. We'll be expanding detectors to go into space. The most well-known is, of course, LISA, which will be an equilateral triangle configuration of satellites that will measure gravitational waves in the low hertz and millihertz bands. This is where we'll see all those white dwarfs in the galaxy. And hopefully this will launch in the late 2030s, but we'll see what happens. There's some other detector concepts, such as DESIGO and TIENGO, that will probe at slightly higher frequencies than LISA, and those will be important later. There's also some indirect detection methods, primarily looking at B modes in the cosmic microwave background. So of course the BICEP group has a lot of people here at Caltech, and there's the CMB-S4 experiment, which I think is still under development. But essentially looking for a signature in the cosmic microwave background that can only be produced by gravitational waves, and thus would be a smoking gun for these inflationary gravitational waves I described earlier. Finally, there's a number of sort of diverse experimental plans within atoms, optical, and molecular experiments. So for example, the MAGIS 100 atom interferometer at Fermi Lab separates the wave functions of atom clouds into two parts, and if a gravitational wave passes through the experiment, there will be a relative phase offset once those wave functions are recombined, and that could read out as a signal from the gravitational wave. There's also an effect called the Gertrude-Stein effect, which allows two gravitons to convert into photons in the presence of a strong magnetic field. So there are plans for high finesse microwave cavities with a strong magnetic field passing through them to sort of look for these very high frequency gravitational waves, converting into photons that would then appear in the microwave cavities. Finally, there's some plans to look for gravitational waves in the high kilohertz band using levitated nanoparticles, optimistically in the 2030s. I'll get more into that later. Okay, thus ends the introduction. Now comes all the random topics. Okay, first, I'll make a case here for high-frequency gravitational wave detection by repurposing existing interferometric infrastructure. In other words, can we take advantage of resonance conditions within optical cavities to search for gravitational waves outside of the frequency bands that these existing detectors are searching in. So if we think about a gravitational wave passing through a cavity, such as the one in LIGO, we generally frame this as the mirror moving with some frequency that is equal to the gravitational wave frequency. Now, as the mirror moves, it creates some time-dependent phase delay in the light that is reflected off of that mirror. We can write this in terms of something called sideband fields, where there's actually a small component of the electric field that has a frequency shifted relative to the carrier light. So, if the gravitational wave, or if the laser light has some wavelength of 1064 nanometers, has some frequency of 3 times 10 to the 14 hertz, there will be electric field components at 3 times 10 to the 14 hertz, plus or minus the gravitational wave frequency. We call these the sideband fields, and the 3 times 10 to the 14 hertz the carrier field. Now, if we consider some interferometers, such as Geo600, an interferometer in Europe that I've depicted here, the differential power at the readout, basically our readout signal, is going to scale as the product of the carrier electric field and the sideband electric field. You can see this by sort of writing your total electric field as the sum of the carrier and the sideband, recalling power as the square of the electric field, and then taking the first order correction from the sidebands. The idea here is that if we can amplify the sideband electric field, we might be able to get more power at the readout and thus better sensitivity to gravitational waves. One way we might do this is by making those sideband fields resonant in the optical system. So in Geo600, there's a cavity formed by the signal recycling mirror, the MSR, and the two mirrors that form the arms of the Michelson interferometer. So light can cycle between the MSR and these two end mirrors, forming some sort of cavity. Nominally, the cavity is tuned so that the carrier electric field is resonant in that cavity. But if we change the position of the MSR very slightly, different frequencies of light will be resonant in that cavity. So in particular, we can detune this mirror in a way that makes the sideband fields of a certain frequency, and thus the response to gravitational waves at that frequency, resonant in this system. So what does that look like if we actually carry this out? In this plot, I'm plotting the sensitivity of GEO to gravitational waves as a function of this detuning angle phi for a number of different choices over frequencies and strains. So what you should notice here is in this orange box, if I pick a certain detuning angle, generally the sensitivity is worse than the tuned configuration, which is this dashed line here. But at these resonant frequencies, the sensitivity gets substantially better than the tuned case. So in other words, what we're doing is we're trading off sensitivity over the broadband here for increased sensitivity in these very narrow bands. You might ask, can we do this in LIGO? Unfortunately, not really. There's a couple distinctions between GEO and LIGO. The most important is that Geo600 does not have these Fabry-Perot arms. In other words, there are no mirrors at these positions, which allow light to cycle back and forth many times within the Michelson arms. And since LIGO has these, the effective arm length of these, the total cavity between the signal recycling mirror and the entire arm is a whole lot longer. You essentially scale up the length of the arms in that calculation by a factor of the finesse, which is very large for LIGO. This basically limits how high we can go with these frequencies, and thus you get stuck with only a small improvement beyond the tuned configuration in brown. But across the rest of the band, it's significantly worse. Okay, so with this concept in mind, what can we do with this? Can we make Geo600 competitive at high frequencies? Sort of. For certain monochromatic sources, such as those axion clouds that I mentioned earlier, if the mass of the axion is within a certain range that is predicted by various quantum field theories, there are some points where the SNR here of Geo 600 measuring for, I think, a week for looking for these signals can actually beat the SNR of LIGO here in blue. This is because we have this sort of very effective narrowband detection at these very limited frequencies. And if we match the frequencies of that narrowband detection against the axion gravitational wave frequency, we can get some improved sensitivity there. The benefits are not always clear, however. So if instead we consider something like subsolar mass black hole mergers, which have a waveform strain that looks sort of like these dashed dotted lines here as a function of black hole mass, most of the SNR is accumulated in the frequency band where LIGO sensitivity is substantially better than GEO's. So there's not really much of an improvement that GEO can offer there with this sort of detuning procedure. And I want to acknowledge Chris Junkin, my surf student from last year, and Brian, who I did this work with. All right, so there is some case for adapting existing interferometers to gravitational wave detection, but what about brand new technologies? In other words, can we introduce new tools that allow gravitational wave detection with tabletop-sized experiments? So here I'll introduce something called levitated optomechanics. This is a experimental technique that has found great use within the last couple decades for very precise force measurements. So how this works is that you put some dipole in an electromagnetic field. It experiences a Lorentz force given by the sum of the Lorentz forces of the individual components, so from the electric field and from the V cross B term. And if we do some Taylor expansion here, use some vector calculus identities, and do some simplification, we ultimately see that there's a force on the object which scales like the gradient of the square of the electric field. In other words, the force scales with the gradient of the beam intensity, and thus the region of highest beam intensity acts as a harmonic well, and thus admits some resonant frequency given by the second derivative of the potential there. So what we can do is, if we have some Gaussian electric field where the beam sort of focuses and then expands, we can actually levitate some small dielectric particles which act as a dipole when an electric field passes through them. These objects can be trapped inside the electric field, or the laser beam there. We can then put this configuration as an optical trap, or optical tweezers, in a vacuum, and we can pump out the vacuum, and in doing so we have a very sensitive force measurement tool, because there's no coupling to ground noise, the number of gas molecules in the chamber is very low, and we can get force sensitivities of 10 to the minus 21 newtons, or better. This is a figure as of like 2015 or something. There's many applications of this technology. For example, we can test gravity at very short ranges by levitating some object in a beam and putting some gravitational source mass, which is this sort of green and yellow striped object here, very near to the levitated object, and then move it around a lot and see how the particle responds, and thus measure the gravitational force. This tool is also being used in quantum simulation arrays, scanning microscopy, where this sort of dumbbell-like object is placed in an optical trap, and as this sort of this sapphire grating is moved along the x direction here, the resonant frequency of that optical trap harmonic potential changes as a function of position. That's this red curve here, and thus you can map out the properties of this grating. Then people are even using levitated optomechanics to study the mechanical properties of DNA and RNA by basically attaching the DNA molecules to some dielectric, putting it in the trap and sort of manipulating it and seeing how it responds to both the laser and the forces that the biological molecule provides. Okay, so how can we do this? Use this technology for gravitational wave detection. So let's consider some optical cavity with a small dielectric placed inside. The electric field inside this cavity forms a standing wave, And because the particle likes to be at regions of highest electric field intensity, it's going to sit at one of the antinodes of the trapping field in orange. Now, if I move, or if I send a gravitational wave through the cavity, the n mirrors of the cavity move by an amount h times L, and the particle is going to move by an amount h times the trapping distance, L sub t. In doing so, when this cavity changes length by a different amount than the distance from the input mirror to the particle, there's actually going to be a displacement between the new particle location and the new location of the antinode. So now your particle is no longer sitting at the base of your harmonic potential, and it's going to be forced in the direction of that new potential. What that looks like is the particle is going to experience some force in this direction as the gravitational wave expands the cavity. This frequency is then just going to follow the time variation of the strain, so it looks like a cosine of omega t if your strain is a cosine of omega t. If you match the gravitational wave frequency, that is the frequency at which this antinode is moving around relative to the particle, to the resonant frequency of that trap, this particle is basically always trying to catch up to the antinode position, but it can't quite get there. So you actually get some resonant amplification of the particle's motion. In fact, the particle's displacement is magnified relative to h times L by a factor of q, which is the quality factor. And for the quality factor of these systems can be very large, like 10 to the 10 or higher. So essentially what we're doing is we're exchanging the very long arms of LIGO and their very high finesse cavities that allow light to cycle back and forth many, many times, amplifying your gravitational wave signals, with a lower finesse cavity, but a very high Q factor transducer. That is, the way that this gravitational wave is coupling into our readout is through the amplified motion of this particle in the cavity. We have a 1 meter prototype that is currently under construction at Northwestern that I worked on during undergrad and I'm still doing some work for today. Just some pictures of an optical setup are kind of cool to have.
Can I ask a question?
Yeah.
So for this setting, there's only one frequency of gravitational waves can be detected through this setup?
Yeah, that's right. For a given trap configuration. Now, what's interesting is the trap frequency scales with the square root of the power of the laser. So we can search at like a very narrow band, and then we can just change the trapping laser power and search somewhere else. So we can actually scan over a long range of frequencies. In fact, a student in our group recently did a study on whether these gravitational waves from axions could be detectable with this sort of setup, and found that once we expand this 1 meter prototype to a 10 meter prototype, the axion signals, which are all these different color curves, they're a function of the axion mass, can actually get higher than the predicted sensitivity, which are these dashed curves. The blue is the 10 meter version, and we might be able to get a detectable signal there, which could be very exciting. Now these curves here are based on the assumption that our noise is limited by classical sources, so collisions with the gas molecules in our vacuum chamber, and the recoils of the trapped laser photons that bounce in every different direction. What I'm working on right now is a complete noise budget that actually takes into account all the quantum mechanics in the very first principles way that I'll be updating these. Yes.
I thought you just said that the sensitivity was relatively narrow band.
Yeah, so this is when we scan over a range of frequencies.
So what's the line width that you have?
So the line width at an individual power will be order 100 hertz or so. These curves here are the signals from the axions. So the plan is you pick some power, you scan here for a week or so, you change, you look again over and over, and you can sort of trace this out. Yeah.
What about the detectors? That's a minimum frequency for where you can, how low can this scan go?
Yeah, so in addition to the power changing the frequency of the trap, it also changes the depth of the trap. So at some point your power is so low that your particle's not going to be well contained within there due to its thermal oscillations. That'll probably be around a few kilohertz, 5 kilohertz. So unfortunately, we probably can't get to the whole neutron star post-merger type signals, unfortunately. Yes?
Is the red line the current version?
Red line is the 1 meter. Yeah, it's the 1 meter version that we're building right now. So of course this is tantalizing, but this red line is sort of heuristic at this point. I'm trying to update it.
Okay, so like if you had a full noise budget, you might probably put it over what you can detect.
Yeah, it might. My hypothesis right now is that the quantum noise contribution in this previous calculation was substantially underweighted, but I am currently trying to compute this correctly.
Is there some dependence of the behavior on like the test mass, or?
So the mass sets the quality factor. But it also sets like the noise that we see from these like gas molecule collisions. Generally, the more massive we get, the better in terms of our strain sensitivity. So we have a group at University of Washington that is working on manufacturing some very extended size particles. It'll be like tens of microns in diameter, a few hundred nanometers thick, and then we're trying to figure out how to trap these. So actually I can go back a couple slides here. What's been used in the past are these little beads that are 100 nanometers in diameter. If I go even further, this is a SEM image from a previous experiment out of the group where we basically fabricated these hexagons that are a few microns across, a couple tens of nanometers thick, but we have figured out how to put these in the trap. So there's some more work to be done, but we're moving in the right direction with this manufacturing problem. Okay. Time for another change. I'm going to switch out of the high frequency and the detection ideas and go to low frequency astrophysics and ask, can we measure external forces on, say, a compact merger environment by their modulations to the gravitational waves that come out of that environment? So let's consider some stellar mass binary, M1 and M2 here, that is in spiraling with each other, but they're also orbiting a supermassive black hole. It's just M3. So they might be in the center of a galaxy or something that's very far away, but they're orbiting this SMBH as they are in spiraling. The second image here is sort of a top view of what's going on here. So in addition to just the orbit around this supermassive black hole, this stellar mass binary is going to undergo a couple different precession effects. The first is paracenter precession, which is what was observed with Mercury going around the sun. So just sort of the overall shape of this elliptical orbit will precess around the supermassive black hole. And the second is called de Sitter precession, where if the angular momentum of the inner binary, that is the stellar mass binary, is not aligned with the angular momentum of the outer binary, which is the binary around the supermassive black hole, this L sub I will actually precess around L sub O. Both of these precession rates scale with the just the Keplerian frequency times the supermassive black hole mass over the radius of the orbit with some eccentricity correction. Now, in principle, these precession rates, along with the actual Doppler motion of the orbit itself, will cause modulations in the gravitational wave signal observed here in the solar system. So if we can actually measure that evolution, we might be able to constrain the properties of the supermassive black hole as well as of the orbit. Now, these effects take many orbits to accumulate, so we need something that can actually measure these systems for a long time. This rules out LIGO for doing any sort of detection like this because we only get these signals for a few seconds. But these space-based detectors like LISA, DESIGO, and TIENGO can observe these systems for a much longer period of time because they look at lower frequencies, and thus they might be ideal for measuring these effects. I've just thrown up the sensitivities of TIENGO, DESIGO, and LISA compared to LIGO here in this plot, along with the sample waveform from a system like this that's experiencing all these precession effects. Okay, so what sort of measurement uncertainties did we get? We lost all my animations, but that's okay. So in this calculation, we just quantified the measurement uncertainties using a simple procedure called the Fisher matrix. which essentially looks at how sensitive the waveforms are to some parameter, theta sub a, computes a noise-weighted inner product, and then inverts this matrix. Essentially what we're doing is saying the more sensitive a waveform is to a certain parameter changing, the better we can measure it. And if we consider these two plots here, where as a function of the supermassive black hole mass in gigasolar masses and the radius of the orbit, I'm computing the fractional error obtainable in this in the SMBH mass and the orbit radius for a 5-year observation window. And generally across this parameter space, we can get accuracies of 10 to the minus 3 or better, which is pretty exciting. Now, there's two main features that sort of determine how sensitive these measurements will be. The first is these trends following these sort of dashed lines here in the lower left corner. In this region, the sensitivity is primarily set by the de Sitter precession. So what's going on here? Well, from the evolution of the Doppler phase in this orbit, we can measure the Keplerian frequency very well just by looking at this time evolution. However, if with just the Doppler motion, there is a degeneracy in the magnitude of the Doppler shift from the radius of the orbit as well as its inclination. So we need to break that somehow to get measurements on the radius and by extension the mass, because they're all related to this expression here. So de Sitter precession allows us to break that because it essentially provides an additional phase on the waveform beyond just the Doppler phase. This phase is often called like the Thomas phase because it originates from Thomas precession, but essentially it gives us another effect in the waveform that allows us to break this degeneracy. Elsewhere in the parameter space, these lines of constant A over M set the measurement uncertainty, and this is the contribution of pericenter precession to the waveform, where the magnitude of the pericenter precession goes like the precession rate times the orbit radius, because your whole orbit is rotating like this, and that gives you a sort of M over A power law there. Now, generally increasing the eccentricity improves the precision. So over on the right-hand side here, I'm looking at the fractional error of the mass as a function of eccentricity, and for the most part, as I increase the eccentricity, our measurement uncertainty gets better, which is good because it's expected because these pericenter and de Sitter precession rates increase the higher your eccentricity is.
And sorry if I missed it. So this is basically just like, so you're computing this, inner product on the top right, but how long does it actually take to make this measurement?
Yeah, so we're assuming a 5-year measurement window.
Okay.
Which is about the length that these missions are supposed to last.
Okay, great, thanks.
Yeah. Any other questions on this before I jump into the last topic? How am I doing on time, by the way?
Maybe 20 minutes, I think.
Okay.
Including
We'll finish in plenty of time.
Yeah.
Yeah, go ahead.
So, do you know anything about like how to calculate the waveform of such like Emery or bi-Emery systems so far? Like, is it only can be done by numerical relativity, or is it can be done by post-Newtonian?
So what I'm doing here in this calculation, at least, is so because so these low frequency space-based interferometers are really only measuring the in-spiral, at least in their particular band. So we can do that just with like post-Newtonian physics. And then so we take a post-Newtonian orbit and waveform. We add in these extra effects due to the presence of the supermassive black hole. So we like artificially put in Doppler phase, de Sitter precession, and all those other things, and then spit the waveform out.
I see.
Okay. Now, for my last topic, I'm going to go back to high-frequency gravitational waves and talk about some tests of GR that are possible in this domain. So here I'm interested in answering how the environment around a compact merger impacts tests of general relativity using the gravitational waves from those sources. All right, so now I have to tell you about black hole perturbation theory in 2 bullet points, which is quite a task. The first is that perturbations to black hole metrics generally solve a separable partial differential equation, where in the radial sector there is a wave equation with some potential. So it's partial with respect to r squared is equal to omega squared minus the potential function. The second bullet point is that the solutions to this wave equation in the radial domain, which are completely ingoing at the horizon and outgoing at infinity, are known as quasi-normal modes, and their respective frequencies, or the Q and M frequencies, accurately fit the ring down of a remnant BH. So these Q and M frequencies are complex. They have a negative imaginary part so that the solutions decrease in time. And looking at this this figure from the first gravitational wave detection, this ring down is the final phase of a compact merger, where once the two black holes have merged into a single horizon, they oscillate and emit gravitational waves until they relax to their final equilibrium configuration, and this looks like a sum of decaying sinusoids. Now, the mass and spin of a black hole uniquely determine its Q and M frequencies. So, if we take data from a compact object merger, and we're able to extract multiple frequencies from the ring down, we can map those to the resulting black hole mass and spin. And if those frequencies are not consistent with one another, that is, one frequency predicts a certain mass and spin, and another frequency predicts a different mass and spin, but there only can be one black hole, what must be going on is that GR must be incorrect. There must be some correction to general relativity that sources these Q and M frequency differences. Or is there? Does it have to be wrong? Well, maybe not. So within the last few years, a number of groups have considered taking this wave equation, which has some sort of long-range potential like this purple curve here, and placing a very tiny bump at large radii in this potential function. They often propose that this bump is sort of a stand-in for some additional mass in the astrophysical environment around this remnant. And they ask, if I put this bump here, how do the Q and M frequencies change? Well, nominally you would expect that, oh, it's some perturbative effect in my wave equation, I should have a perturbative effect in my Q and M frequencies. Actually not true here. It turns out that the Q and M spectrum, that is the space Q and M frequencies for that space-time, can be completely destabilized. What that means is that the Q and M frequencies shift to a degree much larger than any sort of perturbative parameter that you can assign to this bump. What that looks like here is, so in this plot here, all of these colored dots are Q and M frequencies as a function of the radius at which they've put this bump in the potential. So there's sort of this spiraling black trajectory here, which is the trajectory followed by the fundamental Q and M. But as I increase the radius, so here it's 35, 40, 45, 50, new modes sort of emerge from very large imaginary components, which is like very strongly damped modes, and they begin to fill the space of Q and M frequencies in a way that the fundamental mode, which is characterized by the most weakly damped mode, no longer becomes the most weakly damped mode. Some other mode takes over. Now, these original results were a little concerning because, you know, if your Q and M frequencies are totally unstable to some very small perturbation that can be very far from the black hole, how can you expect to sort of perform these tests of GR with these waveforms without a complete understanding of the entire environment around the black hole? Fortunately, the story is not so sad. The time domain ring down signals, when you consider this bump, are generally stable to the bump. So when you actually look at the time domain waveform, the change is perturbative, and you can just continue fitting the ring down with the Q and M frequencies of the vacuum solution. So you're probably okay still doing these tests. Now, what I was interested in answering here is, this bump is sort of ad hoc. the potential doesn't have a great correlation to like actual, sort of matter stress energy distribution, and so this bump is a little contrived. But what if instead I replace this bump with a true perturbation to the environment? Let's actually like put a shell of matter in the space-time and see what happens with the ring down in the Q&M frequencies. All right, so that's what we did. So the picture here is I have some Schwarzschild black hole, and at some radius r, I put some very thin shell of matter, delta m, which is mass, and I give it some speed of sound, v sub s, and I consider how this impacts the solutions to this radial wave equation on the entire domain. Really what it does two things. The first is it imposes some discontinuities in the solutions to the wave equation. These discontinuities emerge from accounting for essentially Einstein's equations with the stress energy that is provided by the shell. And the second effect is that the additional mass of the shell slightly redshifts the gravitational wave frequency in the exterior spacetime. So this is different than having some bump at the potential, but we can then do sort of all the same studies and see what happens. So the first is if I put this shell very far away, just like a bump in the potential very far away, the Q&M frequencies can still be destabilized. So in this plot here, if you look at particularly the green X's, which is a shell radius of 60 m, a shell mass of m over 100, and a speed of sound of 0.5. There are many, many Q&M frequencies in this space where in the vacuum there was just one, which is denoted by this sort of intersection of dotted lines. This is clear evidence that the Q&M spectrum is destabilized. Now, if I make the shell mass small enough, there is always a regime where the shift to the fundamental mode frequency is always perturbative and scales like delta m. This is what you would still sort of expect from sort of perturbation theory analysis. Now, interestingly, there's another feature in this study that does not appear when you just add some bump naively to the potential. Namely, it's a Q&M that emerges directly from the gravitational wave driven motion of the shell. This Q&M has a very small imaginary part. In other words, it's very weakly damped. And that's because the damping of the mode arises purely from the gravitational waves that are emitted as the shell sort of oscillates. So it's purely gravitational quadrupole radiation. And that's pretty weak. So this mode lasts for a very long time. In other words, once a gravitational wave passes through the shell, if its frequency matches the resonant frequency of this shell's motion, the shell gets very strongly excited and then slowly decays due to additional gravitational radiation, secondary gravitational waves. Now, if I actually compute ring-down waveforms, we can see the effects of the shell. So in this top right here, I've taken a shell mass, which is half of the black hole mass, and I've put it at a radius of 6m. And I've then computed the ring-down waveform when I drop some particle directly into the black hole. So the waveform itself is the line in blue, which here is covered up entirely by the orange dashed line. And we can see at late times, there is some very weakly damped component that almost looks constant. It's just some, like almost constant oscillation. And that is this sort of shell ringing mode that I described earlier. If I try to fit the signal with the Q&Ms of the shell system, I get a much better fit, you can see pretty clearly visually, than if I try to use the Q&Ms of the vacuum system. Now, this is not really a perturbative case. I've made some very large shell mass and at some very small radius. So you would sort of expect that it's going to be completely different. If I change this instead to a shell that is very small, it's like m over 100, and I put it at a very large radius, which again is the case that created these destabilized Q&Ms, the ring down looks much more like a vacuum ring down, where it's sort of strongly damped. It follows pretty consistently one frequency as it decays. And if I do these tests of the mismatch between the shell QNMs fitting and the vacuum QNMs fitting, it comes out that the vacuum QNMs fit the signal better, so all is good and okay in the perturbative world there. Finally, if I make a different choice of shell parameters, so if I have some large mass shell and at some very large radius, so sort of combining these two sets, I can actually see that this shell can source an echo in the gravitational waves. So the shell itself can actually be slightly reflected in the gravitational waves. Some can bounce back off of it. And this allows, this essentially creates a cavity where the primary bump in the potential forms one end of the cavity, and the shell forms the other end of the cavity. And the gravitational waves can sort of bounce back and forth in between the two, but very weakly because both of their reflectivities are pretty small. But if I make the shell mass large, its reflectivity goes up, and I can actually see that in the early times, there's a ring down going on, but then later, the strain goes back up before ringing down again. This is essentially what's going on is there were some gravitational waves that escaped the first time, and then some that bounced off the shell, bounced off the central potential, and came out again, and created a second piece of the ring down there. So there's lots you can do with the shell. A lot of it mirrors what's seen with these bump studies, but it's good to have sort of a true astrophysical analog. I'll conclude by just saying that it's an exciting time in gravitational wave astronomy. We're really opening up a large band of new frequencies to study, which should allow us to get a bunch of new exciting physics and maybe some things that haven't even been predicted here. Thanks for your attention.
I think we have time for maybe 2 questions or so. Yeah.
So for the high frequency axion searches, how competitive are the methods that you would have access to, like Geo100 or the tabletop one, versus the current axion limits in these mass ranges?
Yeah. Are you like comparing to like ADMX or something like these other like microwave cavity experiments? I'm not entirely sure. I think so. ADMX is sort of looking for axion fields that are passing directly through the detector, and I think those are more sensitive to whatever coupling strengths you have than what we have. I guess we're sort of doing more of an indirect search, where we're looking for the signatures of these axions at distant black holes. So I think our sensitivity is worse, but we have sort of a larger range of, I don't know, like spatial volume we can look for these things. Yeah.
For your Geo600 detuning proposal, you said that for like subsolar mass objects, it wouldn't be competitive with LIGO because of the in-spiral, but Alan has this thing he wants to propose where you like detune, he proposed detuning LIGO to like hit the post-merger remnant frequency for neutron star, like as you see the in-spiral. Would it be possible to like reactively detune Geo600? Maybe you don't care about the merger of a subsolar mass object who assumes a black hole. But
Yeah. I hadn't really thought about that much. Does Alan think we can detune the Fabry-Perot arms or the SRM? Do you know what he has in mind?
Signal cycling.
Signal cycling? Okay.
Yeah.
I don't know.
But the idea is that there's like a pipe dream that you'd be able to, in the future, you could have a like early warning pipeline trigger a real-time detuning to follow the in-spiral.
I'm just not sure how you get past like the fact that detuning doesn't really help you at kilohertz.
Yeah, but like you have LIGO observe the in-spiral.
Okay, and then you do this.
And then
use
you do
Geo.
this to Geo600, like you observe the in-spiral, predict what the merger frequency will be, then do this to target it.
Yeah, I mean maybe if Geo gets better, like you gotta get like LIGO's down here at 10 to the minus 23 at kilohertz. Geo's improvement only comes once you cross over a couple tens of kilohertz. So doing anything here requires you to push this down like an order of magnitude. But maybe Geo is always trying to get things better, so who knows.
All right, let's thank our speaker again.